Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Yeah. Hi, everyone. We're pleased to have Wahid Liagat speaking today. He's been intern this summer and will be finishing next week. And today he'll speak about some online node-weighted Steiner network design problems.
Thanks, everyone, for coming. I hope that you can hear me, I suppose. So this is a joint work with Malia and my advisor, Mohammed. And this is about online node-weighted Steiner connectivity. So let's just go to the basic definitions, if we can. Okay. So, let's see what's an online problem. An online problem, the requests are coming online, and when you get a request, you have to make an irrevocable decision to somehow serve that request. But this decision should be made without knowing the future requests. Okay? And how do we measure the performance? We say that, we compare our output of the algorithm compared to the optimum, which knows all the requests in advance. So that's why we call it offline optimum. And the competitive ratio is simply the worst case ratio of our cost over offline optimum, the worst over all the input sequences. Okay? So what is node-weighted Steiner Forest? We have a graph with node weights W, and then there is a sequence of pair of vertices Si and Ti, and the goal is to find the minimum cost subgraph which connects every pair. Okay? We can also imagine edge weights, but node weights are more general. You can simply put a vertex on every edge with the weight equal to the weight of that edge. Okay? We also assume that these SITIs, they don't have any weight, or the weight is just 0. This is without loss of generality and only simplifies the explanations. Okay? So this is node-weighted Steiner Forest. For example, if we only have one demand S1, T1, then this would be the optimum solution. If we have S2 and T2 as well, this would be the optimum solution, which can be disconnected. That's kind of why we call it the Steiner Forest. And then if we get S3 and T3, some demands may actually benefit by sharing, and then the optimum solution would change to this. Okay? So what's the online variant of the problem? We know the graph in advance. This is very important. But the sequence of demands are coming online. So after we get a new SITI, we need to augment our solution to actually keep Si and Ti connected. But we can only buy new vertices. We cannot, give back the vertices that we have already purchased. Okay? That's why it's kind of irrevocable, right? And we want to be competitive against the offline optimum. Okay? So let's see some bad news about these problems. So a Steiner Forest, a special case of a Steiner Forest is a Steiner tree in which all the demands share a common vertex, which basically means that we only have a set of terminals and you need to connect everybody to each other. Okay? A special case of node-weighted Steiner tree is the set cover problem, where we have a universe of elements, and given a collection of subsets of these vertices, you need to choose the minimum number of sets such that every element is covered at least once. Okay? And you can see why this is a special case. Essentially, for every element, we put a terminal, those vertices which we want to connect. And for every set, we also put a vertex and connect every set to the elements which are covered by that set. And then we put a special terminal here, and we ask all the terminals to be connected. So essentially, connecting a terminal to the root here means buying one of these sets, right? Also note that set cover is only a special case of node-weighted Steiner tree, because if you have only edge weights, for example, if you move the weight of these vertices to the edges, actually this won't be it won't be a special case, because the cost of the set cover is 2, but now you can actually route all the terminals to the root with only paying 1. Okay, so this is important, that only node-weighted Steiner tree is more general than set cover. Okay? So the bad news is that for the online variant of set cover, you roughly can get a lower bound of log square. So this means that for all of these problems, we have at least a lower bound of log square in the online variant. Okay? So these were the bad news. Let's see what has been the good news before. The first good news is that online set cover can actually admit almost a tight upper bound of log square. And this is due to Alon, Auerbach, Azar, Buchbinder, and Naor. This whole framework can also be generalized to many other problems. For example, non-metric facility location, which is, we will get to this problem later. And then in 2011, Sefi Naor, Malia, and Mohit, they actually developed the first logarithmic competitive algorithm for a Steiner tree, node-weighted Steiner tree, by giving a log square competitive algorithm. Although there is no known generalization of their analysis to a Steiner Forest, and they left the Steiner Forest problem as an open problem. Okay? So what we're going to do in this talk, we're going to give a log cubed competitive algorithm for node-weighted Steiner Forest online variant. And then we are going to give a better competitive algorithm, actually logarithmic competitive algorithm, when the underlying graph is planar, or in general, it excludes some fixed edge as a minor. And then we can show that all the same guarantees, both for planar and general case, carries over when a problem which is more general than Steiner Forest, when the cut constraints are kind of characterized by some proper function, which I'll probably skip in this talk. So we essentially try to design a kind of framework of working with node-weighted online problems to deal with these two.
So sorry, sure. It does not depend on the value of the functions, like for any arbitrary high connectivity as well?
No, it should be a 0-1 proper function.
0-1.
Yeah. Here by proper, I mean 0-1.
Suppose it was, so can you lose a linear factor in the R max or something and get it?
Not yet, actually.
That's open, actually.
That's open, yeah.
Even the edge version needs a lot of code.
Okay.
So even
yeah,
even 2. So I will quickly go over our approach in few slides, and then I will formalize everything from scratch. So first, let's try to give a lower bound for the optimum solution. Let's say that these black boxes are the terminals, and you want to connect them somehow. Let's see how we can get a lower bound. So of course, one way to go is to write an LP and then get the dual. But we don't need to explicitly go to that. We just use the ideas behind the dual kind of vectors that we have. So let's suppose that, for now, suppose that the edges only have weights. And suppose that I'm drawing some disks on every terminal, some of the terminals, such that these disks are non-overlapping. Okay? Then I can claim that the optimum solution is at least the total radii of all these disks. Why? Because the optimum solution should connect these terminals. So this means that for every terminal, the optimum solution should come from outside the disk and reach to the center, which is this terminal. So essentially, the optimum solution has to pay at least the radius of this disk. Okay? So the total radii of all these disks is a lower bound for opt. And of course, I want to make them as big as I can so that I have a better lower bound for opt. Right? But I don't want them to have any intersection, any overlaps. Okay?
So why the disk? You have node-weighted bound?
So
how do you define the disk?
So essentially, we'll get to the formal definition, but essentially means that it starts from the center and just reach to every terminal which is reachable by radius r. Okay, just actually just an intuitive one. Draw a disk, a circle exactly.
You can't define what radius
Yes,
is,
yes,
but we'll get it. All right.
Some radius.
All right.
Every disk can have a radius.
Okay.
Now, if you keep growing these disks, at some point, so assume that these are disks. Well, they're not exactly disks, but okay. At some point, you get into some intersection that if you grow them a little more, then you will have an overlap, right? So at this point, we will see that one natural way to deal with is to somehow connect these centers, these terminals to each other, by connecting them to this intersection vertex. Such a tree, we call them spiders, and this is the center of the spider, the only vertex which can have degree at more than 2. And these are the legs of the spiders. Okay? You'll see a little more about them. So this is essentially the whole disks business that we have. Now let's try to actually design an algorithm for edge-weighted variant. Okay, so we have edge-weighted Steiner Forest, online variant. So one greedy candidate is to just, whenever you get this new endpoints of the terminal, S and T, simply buy the shortest path. But the shortest path considering the previous vertices that you have purchased. Okay, you get a discount. Basically, you get them for free. Now find the shortest path. Let's say the length is D, and then buy that shortest path. And to try to pay for that shortest path, try to put a disk of radius almost D on either S or T. Okay? So you basically get S and T. There is a shortest path D. You buy this path, and then you will try to buy a disk, essentially put a disk over S or T. Let's say with radius D over 4. 4 is just some constant. Okay? If you can do this, then you're really happy, right? Because you satisfied the request, and you put a disk here. So this means that you can charge the cost of that shortest path to the radius of this disk. But the catch is that there might be some previous disks here which have intersection with both of disks on S or T. Okay? So essentially, you won't be able to put this disk without overlaps.
Okay, so are these disks basically the, like, you use the shortest path math rate defined by the weights on your vertex?
Yes. Yeah, exactly.
Okay.
Yeah. You can assume that these are only edge weights. Okay, so it's kind of more intuitive, I guess. So we won't be able to put these disks. Instead, we're going to do something else. We're going to connect S to the corresponding center here and T to the corresponding center here. Okay? So what do I get now? What do I get is that now U of S and U of T are actually connected in my current solution. Right? They may have been connected before, but now I'm sure that they are connected. Okay? So what I'm going to use, somehow I want to use this fact. How I'm going to say that, okay, assume that the radius of these disks have been also the same. So almost all the disks have the same radius, D over 4. Okay? Then I can say that this path that this extra path that I'm buying, the length of them is at most D over 2. So this means that if U of S, U sub S, and U sub T have been already connected, I have a contradiction. Why? Because I said that the shortest path between S and T is D. But if these guys have been connected in my solution before, then I can go from S to here, paying less than D over 2, then jump to UT with the vertices that I've already purchased, and then go from UT to T. So this means that my shortest path is actually less than D, which is a contradiction. Okay? So by actually doing this, I'm sure that US and UT have been connected exactly in this instance, in this step. Right? So this means that if I keep all the disks with the same radius together, then every time that I have such an iteration that I cannot put a new disk, I'm reducing the number of connected components. These two have been disconnected, now they're connected. Okay? So what I'm going to do is that for every power of 2, for every radius of power of 2, I'm going to have a layer such that all the disks in that layer have the radius 2 to the I. Okay? And then whenever such an iteration happens that I won't be able to put a new disk, I'm reducing the number of connected components. So this means that I can charge my cost either to the new disk that I'm putting, or if I'm not putting a new disk, I can charge it to the previous disks, because I can only reduce them by the number of disks that I have, right? So that's one way that you can actually solve the edge-weighted variant, which is due to Berman and Colston. Okay. And let's see what goes wrong in the node-weighted variant. In the node-weighted variant, the issue is that, okay, you can do the same thing by the shortest path, and then try to put a disk. But now the intersection happens on the vertices. So you may get into intersection with many disks at the same time on one single vertex. Okay? So the natural generalization would be to buy these yellow spiders and then hopefully say that, okay, I'm reducing the number of connected components and the same analysis, right? But this doesn't happen because this intersection vertex might be very expensive. It might be the cost of all this spider completely concentrated on this vertex. So this means that S and T might actually be far from each other because we have not purchased these intersection vertices before. So we cannot say that these guys are disconnected. They might be actually already connected. So even if you buy these spiders, you may not be reducing the number of connected components. So this argument fails. But let's say if it actually fails, I mean, how can we fix it? So for example, if this degree is kind of constant, this yellow degree, the number of legs of this spider, if it's constant, then we can almost do the same trick, right? Instead of d over 4, we put d over some bigger constant. So the nice thing is that if the underlying graph is planar, we can argue that the average degree of the average, basically the number of legs, is constant. So somehow you can actually amortize over the whole number of disks, such that you still can pay for all the paths that you're buying by charging them to a number of disks. That's how we will see that we can do it for planar graphs. But for the general graphs, this completely fails. I mean, there is no bound on them, which means that we cannot just greedily buy these both spiders. So we need to be more smarter. Essentially, we need to buy some of these intersection vertices to somehow keep the connectivity structure on them. Okay? To do that, we essentially are trying to open a facility on these intersection vertices and then connect the close disk to essentially this intersection vertex, right? So this is the whole idea, that the relation between facility location that we'll see later, with the idea to somehow buy these intersection vertices a little smarter. Okay? But then there are the catch is that it's not just the yellow spiders that we are buying. We are also buying this shortest path. So we need to make sure that this kind of facility location needs to pay at least this much, D, so that we can charge the cost of our shortest path also to this facility location. So this was the whole framework for kind of going to this problem. But let's formalize everything by starting from disks. So we formalize them as a kind of painting. We say that every vertex has an area equal to its weight, and a disk of radius r from a center T essentially means coloring every area which is reachable by distance r from that center. Okay? Note that we are assuming that terminals have weight 0, so the centers always have weight 0. Don't worry about centers. Okay? And then just to name some vertices that will be useful, we say that the continent of the disk contains the vertices which their distance to the center is less than the radius. Okay? And so these would be these are the vertices which are closer to the center than the radius, and the other vertices which their distance is at least the radius, and they are partially colored. they will be on the boundary of the disk. Okay? So every vertex on the boundary is at least partially colored. And the vertices.
What does it mean? Sorry. So you say it again. So what is this boundary exactly?
So the vertices inside are those which their distance to the center is strictly less than the radius.
Okay.
Those on the boundary are those which their distance, essentially minus their own weight, is less than the radius, but the radius cannot exceed their distance.
Oh, okay.
Okay. So it's just trying to formalizing the intuition about a disk. I mean, what's meaning to go over with radius r. Okay.
And you can assume that the centers are all zero because you just buy SITIs no matter what. So you can just
Essentially,
so
you
don't
can
have
add
to-
even dummy vertices. Yeah. This is
okay.
without lots of generalities. So
Yeah.
nothing important. Okay. Now let's, for example, at some point, we have multiple disks on one painting, and we say that these are non-overlapping if you are not overcoloring any vertex. Okay. And then, if, for example, one vertex goes tight at the intersection of multiple disks, we are interested in this binding spider, which essentially connects the intersection vertex to the centers of those disks. Okay?
When you say a disk, you also include the boundary.
Yes. Well, disk essentially is this coloring, this painting that you put there. Okay?
And what does it mean to overcolor?
Means that you color one vertex more than its weight. I mean, a vertex kind of has an area equal to its weight, right?
This is a kind of like a dual.
It's just, well, a disk is essentially a function, right? Function which colors some portion of every vertex, right? So if you put these disks to each other, you will color more of a vertex if
But
it's
essentially, it's like
common.
a packing of these, like in the dual.
Essentially, yeah.
Right. So
You can also give a dual interpretation. These are
Right.
actually dual objects, but
Right.
we just don't want to go to the primal-dual world.
Yeah, I understand.
Yeah.
Yeah, just to.
So we call this binding a spider when some vertex at the boundary goes tight. Okay. So, and as we talked, for example, if you have, suppose that all the disks have the same radius r. For example, if you have C disks, then C times r is the lower bound for opt if they are non-overlapping. And also, for example, if you have a binding spider which is at the intersection of, for example, 3 disks, then the cost of this binding spider is 3 times r. Because from the center of the disk to the intersection vertex is just r. Okay, and everything is tight, right, in a binding spider. So these are some things that you can verify by just looking at the definition of the disk. Okay? So let's go to the algorithm. The simpler one is for planar graphs. Let's go with that one. This can be also generalized to H- free graphs. Well, I'm sure most of you know the definitions, but just to be sure, we say a graph G is H- free if you cannot, basically, however you contract an edge or remove an edge, you won't be able to reach from G to H. Okay? A famous example, famous family is basically planar graphs. And there are many interesting properties about H- free graphs when H is a fixed, for example, constant size graph. The most important one that we are working with in this paper is that the average degree of H- free graphs is actually constant. Okay? For example, for planar graphs, we know that it's at most 6. Okay? So I'm just going to explain the exact algorithm for H- free graphs. It's the same idea that we had before. So we get these new terminals S and T. You find the shortest path between S and T, but of course, with getting discount from the previous vertices that we have purchased. Let's say that the distance, that minimum distance is D. Then we buy this shortest path, so we will satisfy this demand. Then we choose the layer I, which is roughly D over some big enough constant mu. Okay? This is just some big enough constant. Don't worry about it. So we choose that layer I. We have these layers of powers of 2 for radius of the disks. So layer I will contain disks of radius 2 to the I. Okay. Then we buy the shortest path, and then we try to put a disk centered either at S or T. If I can put a disk there without any overlaps, then I'm happy. That's it. But if both of them are unsuccessful, I'm going to buy these binding spiders at the intersections that happens. So to just see it, let's say that S and T are the new terminals, and their distance is D. Okay? I will buy this shortest path. I'll try to put a disk of size roughly D over mu, either on S or T. If I can put it without any overlap, then I will just put it there and I'm happy. I will be able to kind of charge my cost to the radius of this disk. But if it's not possible for both of them, then this means that there are some intersections here, right? Both here and here. I'm just going to buy both of these binding spiders. For example, here, this is one binding spider, and this is the second binding spider. Okay? That's the whole algorithm.
So, but you might not intersect at just one place. You might intersect at many places.
Yes, just pick one of the intersections, and that will be my intersection. Yeah.
Do you know that the second step is necessary?
Buying this binding spider?
Yeah, I mean, is it possible with only...
Oh yes, if it's greedy, then it's not competitive, it's uncompetitive, yeah. Because if you don't buy these binding spiders, then you're just buying shortest paths. So this means that you're greedy. And the whole idea is that when you buy these extra binding spiders, you're kind of giving discount to your future self that you will be able to actually go with shortest paths there.
Because for the edge version, it's not necessary.
Yes.
I mean, you lose a little bit in the competitive ratio, but it's still...
Yeah.
But for set cover, I guess, no.
For set cover,
Yeah, set cover, yeah, but this is why, actually, the edge version is not a special case of...
I mean,
The
that's
set cover is not a special case of the edge version.
That's the set cover lower bound doesn't quite hold here. It's only the planar case.
Okay.
But yeah, still, you cannot do better than log in general, and the shortest path still fails. So let's see how we can analyze this. Again, if we want to just charge the cost of all these paths that we are buying to the radius of the disks, now I can assume that we only have log n layers. I mean, you can scale down stuff so that you only need to keep log n layers. And then if I can actually successfully charge the cost of my algorithm to the radius of the disk, this will give me a log n competitive algorithm. Because every layer would be a lower bound for opt, and I only have log n layers. Okay? So,
Yeah, sorry. So could you just repeat? So how do you do one step? Like.
okay, so
Yeah. So what happens?
you buy this shortest path
Okay.
completely.
Okay.
Now you try to put a disk of d over mu in the layer which is for d over mu, right? So you essentially put a layer I such that mu times 2 to the I is less than or equal to d. Okay? So you go to your layer and you try to put a disk on S. If it
Okay.
doesn't have any overlap, you're done.
Okay.
If there is an overlap, you try it for T.
Okay.
If it again, if there's an overlap, then you will just buy these binding spiders. That's it. You don't put any disk. Instead, you buy these binding spiders.
And what is a binding spider again?
If you cannot put a disk on here, this means that there's an intersection with previous disks.
So what is the center of the spider that you buy?
At the intersection vertex. Intersection vertex is caused by putting a new disk with previous disks. Okay. So if you want to buy, essentially put a new disk here, then you will get into intersection with these two previous disks, for example, at this vertex. You may have different intersection
So
points.
which terminals are involved in buying the spider?
these centers of the disks which are touching this intersection vertex.
So for on which it is on the boundary.
Yes.
And the new one of the
And of course the new one S and T. I mean, those are always there.
You may intersect, separate sets, no?
take anyone. Doesn't matter.
Anyone doesn't, not all. Just anyone.
Yeah, just one single
Well,
vertex, one intersection vertex for S, and one intersection vertex for T. So now my total cost is the cost of the shortest path that I'm buying plus the possible binding spiders that I may buy. Okay? So if I can, so I have two different iterations, whether I can successfully put a disk or I would need to buy binding spiders. If I can successfully put a disk, then I'm happy because I'm putting a disk of roughly radius D. I'm only paying D, so I can charge it. That's good. But I may be buying these spiders. There are two cases here. The first case is that one of these spiders is expensive. It has many legs. By many, I mean it has at least mu legs. Okay. The second case is that both of these spiders are cheap. They have at most mu minus 1 legs. Okay? So I distinguish between these two different cases.
So just to make sure, was it what, like, so in terms of all of these parameters, what's the cost of the spider? Is it 2 to
So
the
the
i
cost
times
of a
mu,
spider
or
is essentially the number of legs times the radius. That's an upper bound, because this might be very close to the intersection. Okay. So essentially, when
So if it
both
has one number of
spiders,
legs, then it's good.
exactly, when both spiders are cheap, this means that this whole spider's business is just a constant times D. Essentially,
So
constant
mu-
times
mu is a
radius, which
constant?
radius is D.
Mu is a constant.
Mu is a constant, which is related to the average degree of my
Oh, I
planar
see, I see.
or H-free graph. But it's a constant. Okay. So exactly, if both spiders are cheap, then I can use the same argument as in edge-weighted and say that I'm actually reducing the number of connected components. Basically, I'm definitely connecting all these previous disks to each other, but when they are constant, I can claim that these guys have been actually disconnected before. Otherwise, there would be a contradiction with the fact that my shortest path is D. So this can be dealt with like the edge-weighted variant. That's fun. The catch is that when I'm actually buying an expensive spider, so the way to deal with it is to show that the total number of legs of all these expensive spiders that I buy in layer I, for example, is at most the number of disks in that layer, O of that one. If I can show this, then I can say that, okay, the total cost that I'm paying for expensive spiders is the number of their legs times the radius R. If I can show that the number of legs is in O of the number of disks, then I know that I already have essentially R times the number of disks as a lower bound for opt, right? So then I can relate it. I can still amortize the cost of the legs to the radii of the disks. Okay?
And for that, just average degree is not sufficient.
No, you need it to be,
Yeah.
you need to contract them. So that's why we need H1F. So it's just proof by picture why we have that. So these are my disks, and assume that these are non-overlapping. Well, it's a little hard to draw those. The blue vertices are the centers of the disks in my layer. The black vertices are the centers of the expensive spiders. And the legs are these kind of black kind of edges. Okay? And these are the new unsuccessful terminals that were trying to put a terminal, but I had this issue. Okay? So I know that these are expensive spiders, so this is at least mu number of legs here. So first I'm going to ignore this one extra leg which is connected to S and T. I can double charge it to the other edges. That's fine. Now we'll use the fact that if you have non-overlapping disks, this whole intersection, these intersection vertices are only on the boundaries of these disks. You can check that because an intersection vertex is shared between two disks, and a vertex inside a disk cannot be shared with another disk, because when you're inside, you're fully colored with that disk. Another disk cannot have any share in you. Okay? So these black vertices are actually on the boundaries. So what I'm going to do is to just contract all the continent of every disk to its center. Okay? And then what I have is just a bipartite graph between the centers of the disks, blue vertices, and the centers of expensive spiders. What I want to do is to show that the number of legs is in O of the number of blue vertices. Because blue vertices are the number of disks, legs are my expensive spiders. That's the whole thing that I want to show. Right? And it's easy.
And that's similar to the analysis of the non-online version, kind of, right? Like
the Goldman's Williams?
Yeah, even the Goldman's Williams, I think.
So essentially when you have, almost all of the network is on H-3 graphs, you need to use exactly this pattern. Okay, if you contract them,
right,
you're still H-free, so you have this nice property that the average degree.
Right. But yeah, so these bipartite graphs, basically I think it shows up in the Klein, the main, and Hajjahari.
Yeah.
Okay.
Okay. So the average degree is at most alpha H for all the graph, so still H-free. The black vertices, their minimum degree is alpha H. These are expensive spiders, and number of legs is at least alpha H. So this means that the blue vertices, their degree is at most alpha H. Because in average it's alpha, one side of my bipartite graph is at least alpha, every single one of them. So the average of all these blue vertices is at most alpha. So if I have a bipartite graph such that one side, its average degree is constant alpha, this means that the number of edges, the number of legs, is at most O of the number of blue vertices. Okay? So the number of these expensive legs is at most in O of blue vertices, and that's why I can essentially charge the cost of all these expensive edges, expensive legs, to the radius of my disks. Okay?
So the three black nodes are black nodes at a different time for the algorithm?
Yes. Yeah.
It's not at the same time?
Yeah. At the end of algorithm, just consider every layer, we have this kind of picture here, this bipartite graph here. But this is for every layer separately, because the radiuses cannot be mixed. So that was for the planar. Now, let's see what we can do for the general case. Okay. So as I promised, this has something to do with non-metric facility location. Let's define this problem. In non-metric facility location problem, we have a set of clients and a set of facilities, each with an opening cost. If you want to open the facility, you need to pay this much. And every client, if you want to connect it to a facility, you need to put the weight which is written on that edge. Okay? And then some of the clients are active, which essentially means that you need to connect those clients to some open facilities. For example, if you want to connect all the clients in this problem, then the optimum solution would be this. You need to open facilities here and here, and then buy these edges. Okay? Well, nice thing is that the kind of general approach of Allen et al., you can get a log square comparative algorithm in the online variant of this problem. Okay? So we'll use this algorithm as a black box. So let's see how we want to do this. Come on. So, given a network and a radius r, I'm going to introduce an r-bounded facility location instance. I just call it RBFL. the way that follows. So, for example, let's say I'm trying to make a 4BFL instance. What I do is that for every terminal here, I'll put a client. And for every other vertex, I'm going to put a facility. The cost of opening a facility would be simply the cost of that vertex. Okay. Now the radius comes in play. When the radius is, for example, r, for every terminal, I'll put a disk of radius r on that terminal. And I'll connect the center to the boundaries of the vertices on the boundary of that disk. For example, here the radius is very small, it's just 4. So the vertices on the boundary of this disk is this 5 and 6. And for this disk, it's just 5. The cost on the edge would be simply the shortest path from that terminal to that vertex, excluding the cost of that vertex. For example, here it's all 0 because the radius is very small. For example, if you consider 8BFL instance, again, for every terminal you have a client, for every vertex you have a facility. Now you put a disk of radius 8 over T1. The vertices on the boundary are 3 and 4. So you will connect T1 to these two. And the cost on every edge will be the shortest path of T1 to that vertex, excluding its own cost. So for example, for this guy, the shortest path would be through the 5. For this guy, the shortest path would be through 6. Okay? So for example, I'm sure that the cost on these edges is strictly less than 8. Right? Because a vertex on the boundary, the distance for reaching it should be at most r, should be such a less than r. Okay? And then for T2, I will do the same. I will put a disk of radius 8 over it. Let's see who's on the boundary. This 3 and 4. And the shortest path to them is just 5. So this would be my RBFL instance. Okay? Clients will be terminals. Vertices will be facilities. And for every terminal, I put a disk of radius r and connect it to the vertex on its boundary. Okay? So that's just formalizing what we had in the previous slide. This is my RBFL instances. Okay? In my algorithm, I'm going, instead of having log n paintings, I'm going to have log n layers of RBFL, such that for every I have a 2 to the I BFL instance. Okay? These are going to help me essentially buy these kind of spiders in some sense. Okay? So my algorithm, how it's going to work is that I have this graph and my 2 to the I BFL instances. Whenever I get a new terminal Ti, I will buy the shortest path and do some process here. Then, if a condition holds, I will give this new terminal to one of my BFL instances. Then I'm going to use the log square comparative algorithm as a black box to solve this BFL instance. And whatever that algorithm does in that BFL instance, I'm just going to mimic it in my solution. So if it's going to open a facility, I'm going to buy the corresponding vertex here. If it's going to buy one edge, I'm going to buy the corresponding path in my solution. Okay? So that's how it's going to work, my algorithm. Okay? Now I want to say that what is this condition? That only sometimes I kind of consult with my BFL instances. The condition is a kind of neighborhood clearance, which is kind of symmetric to the fact that, so we are always trying to put a disk, right? If it was not, if there wasn't any overlap. Here, we have the same kind of situation which we kind of call it neighborhood clearance. It's some kind of having no overlap. We say that giving a terminal t to layer I, it has a neighborhood clearance if first there is no open facility close to this terminal, this client essentially, and this client is at least 2 to the I plus 1 far from all the previous clients which have arrived at that instance. If these two conditions hold, then we say that, okay, there is neighborhood clearance for giving terminal t to this layer. Okay? And if this clearance fails, this means that there is either one open facility close to that client, or there is one of the previous clients close to that guy. We call that either open facility or client. We call it the witness of this failure. Okay? So should I go over it again, the neighborhood clearance? So we are
So I guess now this is for the special case of Steiner trees. You're describing it for Steiner.
no, Steiner Forest in general version.
Okay, but then you have this condition at both terminals.
Yes. For now, it's just one terminal trying to go to layer I. If I want to give it to layer I should have neighborhood clearance. It is something like saying that there is no overlap somehow. Okay. Now, what is my exact algorithm? So, my algorithm is the same, that has completely the same spirit. We say that you give me new demand S and T, find the shortest path with length D, by that shortest path. Now, try to give either S or T to the layer I such that, layer I such that the radius is roughly d over 4. Right now, mu is a very small constant, just d over 4. Okay? So essentially, if either S or T, either one of them, has neighborhood clearance in that layer I will give it as a new client to that layer, and then just mimic the solution of that layer. Otherwise, this means that both of them, essentially, none of them have any neighborhood clearance. So I will buy the path from S and T and connect them to the corresponding witnesses. Okay?
For the weaknesses.
So the witness, if you don't have neighborhood clearance, this means that something is near to that, something is close to that vertex. Either an open facility or one of the previous clients in that layer. The witness of failure is that vertex, which is too close to that guy.
So
Too close means actually 2 to the I,
yeah,
at least.
Okay. Back up one slide maybe to see what's new.
Okay.
Oh,
So one of these two is failing, right? So this means that there's already an open facility there, or one of the previous clients in that terminal is too close. Okay?
Okay, sure.
And that thing that is close is the witness of my failure. Okay? So if both of them are failing, I'll just connect each one to its corresponding witness. Of course, there might be many witnesses, but just any of them, one of them. Okay? So that's the whole algorithm. So let's see let's just put some names on these kind of terms here. The first thing is that for every layer I, I'll define the optimum solution, offline optimum solution for that BFL instance as opt sub I. Okay. And the online essentially mapping for that BFL instance, I'll call it M sub I. Essentially the mapping that my online black box algorithm is buying, that is MI. And then I will say an iteration is type I if I'm giving my clients to layer I. Essentially 4 times 2 to the I is less than D. Mu here is just 4. Okay. Now how I'm going to prove this is by just proving 2 facts. First, I'm going to say that opt sub I for every layer is actually a lower bound for the optimum solution to the Steiner Forest. This will be easy if we just prove by picture. Next, I'm going to say that the total cost of type I iterations are closely related to the cost of my mapping in every layer. Okay? Now, note that if I can prove these two, then I'm done. Then I have a log cube competitive algorithm. Why? Because the cost of my type I iterations would be...
So what is this? Am I the online mapping for layer I?
So at each time, there is a mapping of clients to facilities in every layer. So the online algorithm for facility location is connecting the clients to some of these facilities, right? So it's kind of a mapping.
Oh, so is it fine for BFL instance?
Yeah.
Okay.
So both of them have this sub I. So these are about BFL instances.
Okay.
The offline optimum of the BFL instance and the online solution for that BFL instance.
Yeah.
Okay. So if I prove that cost of my type I iterations are bounded by cost of mi, then I know that because of that black box, the cost of mi is at most log square times opt I. And by this lemma here, I know that this is also less than log square times opt. So the cost of my type I iterations would be at most log square times opt. And I have at most log n layers. So I would get a log cube, right? So I just need to prove these two. The first one is easy, just to show that opt is less than opt. Then we go over for this one. Okay? So first, let's try to show that the optimum solution for every facility location instance is actually less than the cost of my Steiner Forest. So let's say that these are the clients in my facility location instance. And I have these disks of radius 2 to the I. Of course, they may have some overlaps. I mean, if you just put a disk of radius 2 to the I, they may have overlaps. That was the whole issue. But if you have an overlap, since at every time that we get a new client, we have neighborhood clearance, this means that these centers, they're at least 2 to the I plus 1 far from each other. That was the condition of neighborhood clearance, that the two centers should be far from each other. When they are far from each other, 2 to the I plus 1, essentially twice the radius far from each other, the only intersections that can happen is on the boundaries. Yeah. Which fortunately, I have one possible facility for every vertex on their boundaries. Right? So just consider the optimum solution for the Steiner Forest, which is connecting these centers. So it's coming from outside every disk and reaches inside, right? So what I'm going to do, I'm just going to give a solution for my facility location by just opening a facility wherever this optimum solution is touching a boundary of one of these disks. I'm just going to open a facility there. And then I'm just going to connect the center of every disk to one of the open facilities on this boundary, according to op. So now this would be a valid and feasible solution for my facility location instance. So of course, opt I has cost less than this. So opt I is at most opt. Good? Any questions about this? So if you just give me any optimum solution for a Steiner Forest, it's touching every boundary. So I'll just open a facility on that boundary, on those intersections, and then I will just connect the center to one of the vertices. This would be a valid, feasible solution, so opt I is less than opt. Okay? So all that remains is to show that cost of type I iterations is at most the cost of the online algorithm for that facility location instance. Then I'm done. Then I have a log cube algorithm. So again, my total cost is the cost of the shortest path and the possible paths to the witnesses, plus the cost of simulating the facility location instance. So by definition, the cost of simulation is the at most cost of mi, because I'm just going to buy everything that mi is buying. So of course it's less than that. Okay. Now to show that these two costs, the sum of shortest path plus the path to the witnesses, is at most 2 to the I. So remember that 2 to the I is essentially the cost of d, the shortest path, the radius of these disks. Okay. To show this.
Yeah, sorry, just want to highlight the effort that you put into these slides by mentioning that the color coding is not random at all, right? So the green color is equal to the sum of these two things, and the two things are blue and yellow. So if you add the spectrum of blue and yellow, you get the green. There is a bonus minion to this.
So, thanks. So yeah, so I need to prove these two facts to essentially show that the total sum here is 2 to the I. These two facts are first showing that the number of type I iterations are actually in O of the number of clients in layer I. So even though sometimes I don't give a new client, it's still fine. So still the number of type I iterations is kind of O of number of clients in that layer. And then I will show that every time that I give a new client to that layer, this mi incurs the cost of at least 2 to the I. If I can show both of these iterations, both of these kind of facts, then I know that, okay, the total cost that I'm paying here is some constant times 2 to the I. Then I get that, okay, so these are in O of the number of clients, and for every client, mi incurs the cost of at least 2 to the I, so I'm done. So let's see these two facts. Actually, the second one is easier. The fact that mi incurs a cost of at least 2 to the I. Why? Because every time that you get a new client, you have neighborhood clearance, which means that there is no open facility close to this guy. So if mi is going to connect this new client, it has to open a new facility and also buy the edge connecting it to that open facility. But this means going from the center of a disk to one vertex on its boundary, and also buying that vertex. So this would be at least the radius of that disk, which is 2 to the I. So whenever you get a new client in that instance, mi has to pay at least 2 to the I. Okay? Because it has to open a new facility and connect it to that terminal. So I'm good for here. Now I just want to show that it just remains to show that the type I iterations are actually in O of the number of clients. How I'll do that is just saying that, okay, the good thing is that if there is a witness, it's either an open facility or someone close to me. If it's an open facility, it's already purchased. So if I want to get connected to it, I need to pay less than 2 to the I, because it's on my boundary. Boundary of disk of radius 2 to the I. So my path to it is less than 2 to the I. And if it's some other terminal which is close to me, so I know it's close to me, so again, I need to pay at most O of 2 to the I to connect to that guy. Okay? So for S and T to get connected to their witnesses, you pay at most 2 to the I. So this means that if these two witnesses, if they are actually connected before this iteration, then I have a contradiction. Because if you put these 2 to the i's together, this will be less than d, my shortest path. So actually, whenever I have this iteration that I actually bypass to the witnesses, I'm reducing the number of connected components. So again, I can do the same old argument and saying that, okay, I can pay that with the disks here. So the number of actually iterations that I do are actually equal to O of the number of, actually at most twice the number of clients in that layer. Okay? So for every type I iteration, my cost is in O of 2 to the I, and mi is also paying almost 2 to the I. So my cost is bounded to the cost of mi. Now, since my cost is bounded to the cost of mi, I know that because of the property of my black box, it's bounded with a factor of log square to the cost of my optimum solution. So this means that I pay at most log cube because I have log n layers. Good. So just to wrap up, so we are using this disk painting as framework, which helps a lot in simplifying the node-weighted kind of Steiner connectivity problems. This might help us in some other problems. Also, you can also generalize these results for price collecting variant.
So when you say this painting, you mean something more than just primal-dual in some sense, or what? Like
It's primal-dual. It's complete primal-dual. But
is it like the synonym that you can?
Well, one fact is that you shouldn't. So one thing that we kind of insist on it is that you shouldn't merge these modes. So you usually have these dual modes that you merge them to each other, and that makes things very hard. Things get complicated, and that would be hard to analyze. Essentially, the whole thing that we're insisting here is that these disks, you don't need to mix them, especially for node-weighted. And this actually helps in some sense. That's the whole thing about difference. That the thing that we are saying that is new compared to the normal mode growing.
When you need to do that, right?
Essentially, connect them with these bunny spiders. Don't merge them in this sense.
Right. Okay. I see.
And that's. Thank you. So, if any questions, any part.
Any more questions? You asked quite a few. Yeah. So, but it doesn't generalize directly to Rmax. Like, I guess maybe I'm just repeating my question from
Not
straightforwardly.
Yes.
So, what is more
So the
for
offline
connectivity
algorithm
is
is good, right?
connectivity? Huh?
No, not for edge.
Offline, no, it's not straightforward.
No.
No, it's just.
The
You only have it for two connected, I guess.
Did you lose like Rmax or something? No?
Yeah, Rmax. Actually, you can
But
get
that's
log
not
of Rmax also.
And you can get log on that.
No, but even Rmax is not, it's not.
I think
straight.
Rmax
It's not-
has to be log of Rmax is not tricky. But here, like for edge connectivity online,
No, not edge. Okay, so for edge costs, firstly.
edge cost, sorry, yeah,
So
edge
yeah,
cost.
so edge costs, there is
You're doing
a
edge connectivity anyway, yeah.
yeah. So
No,
there
there's
is
a
a
paper
recent
from
paper.
Gupta,
Yeah, there's a paper by Anupam Gupta and others, which does it, but it uses structure that weights don't have. So for example, it uses metric embeddings and so on.
Oh. So it works for all high connectivity or only for?
It does, yeah. I think it gives R max.
There is a kind of for node weighted.
What is node offline? So node weighted?
For offline node weighted, you can actually get,
You can
I guess,
get roughly R max, but it's complicated. So
and it's not exactly primal dual really. I mean, it's kind
But
of
it does depend on Rmax.
yes,
Yes.
it's a paper by Nutov. So at a very high level, what it does is comes up with a generalization of spiders to K connectivity, but it's a very complicated generalization. So to work hard.
Okay. Yeah.